Humans have existed on this Earth for 300,000 years, and in that time, we've destroyed it. And so we set our sights on Mars, the red planet, 140 million miles away. Of course, it's not that easy. There are multiple issues associated with this. However, Polaris has considered all of these.
Thank you, narrator. Let's address each issue one by one. However, let's start with our constraints. Let's start with how we'll be able to breathe in the dark vacuum of space. Mars has an atmosphere of less than 1% compared to Earth's. Safe to say, we can't breathe in the Martian atmosphere.
Although we have spacesuits, the demand for comfort on Mars over 10 years means we needed to create breathable atmospheres on our shelters.
Now, most oxygen on Earth isn't produced by rainforests, but rather by a microscopic sea organism called phytoplankton. These little guys are making about 70% of the oxygen on Earth, so they're basically doing most of the heavy lifting for oxygen.
So how about bringing them to Mars? Phytoplankton need light, CO2, and micronutrients to survive, and they only live for a few days. So how would we nurture them?
Easy. Phytoplankton are easy to nurture, only requiring phosphorus, iron, and nitrogen. And because of their quick breeding cycles, their short lifespan won't be an issue. We'll utilize large bioreactor tanks, pressurized so we can collect their oxygen, then distribute it around the colony. And we can scale easily by simply connecting new facilities to the tank. With phytoplankton, our oxygen problem is no more.
Another issue is the exposure to ionizing radiation on Mars, along with the freezing temperatures. Because Mars's atmosphere is over 100 times thinner than Earth's, we're exposed to a lot more radiation than on Earth.
Well, I would hate to be freezing in the shelter.
Agreed. That's why insulation and in-situ concrete are so important. We plan to have many systems in place to keep energy in, from sensors monitoring the pressure inside buildings to the use of concrete made of regolith.
In addition, we can utilize the extra heat from our energy producer, which is a secret for now. Humans need food and water to survive. In a 10-year mission, it really isn't feasible to live off of food brought from home.
That means we're gonna have to grow food and find water.
Starting with water. Surprisingly, Mars has water. This can be found at large areas of permafrost at Mars's poles. Here, we can use a Rodriguez well, which melts the ice and then transports it.
It isn't that easy. Water on Mars isn't ready for human consumption. It will need to go through a thorough purification process. Thankfully, we already have that on Earth, so it'll be easy.
Next, we have the question of food. What could we nurture on Mars for food?
Well, it's like every other sci-fi movie. Potatoes.
Of course, duh, we planted it to the Martian soil.
Not quite. We'll have to make a hydroponic system, basically meaning that the potatoes will be floating in fertilized water.
Sounds nasty.
Well, it can be layered and expanded. Although the biggest problem would be ensuring that it cannot fail, we've already put sensors to monitor everything from water to the nutrients.
Furthermore, we would have to find a way to cycle water and produce fertilizer. And that can easily be done with a water grid and the purification of human feces. A huge issue is the need for energy. For context, the average person uses 10,000 kilowatt hours of electricity every year. Multiply that by 80 people and 10 years, and you can see that we'll have a big problem.
In addition, energy usage will likely be higher due to all the complex systems in place. We need a power source.
How about solar panels?
On Mars, the poles barely get any sunlight. If we were to use solar energy, we would get a minuscule amount. Or we would have to grid panels at the equator and route them back to the poles. That does not sound feasible.
True, so what then?
Nuclear energy, of course. Mars has a very interesting material called thorium. Thorium is a very good source of nuclear energy because it's 4 times more abundant than uranium, and it's very energy dense. However, it isn't fissile, it's fertile, meaning we can't use it to jumpstart the process. We'll have to bring plutonium with us to jumpstart operations, and in about 6 or 7 years, we'll be able to fully sustain ourselves on thorium.
Doesn't nuclear energy have waste?
Not in this case. The difference is that liquid salt thorium reactors can burn up their own long-lived waste products, leaving behind byproducts that drop to safe radiation levels in hundreds of years instead of tens of thousands.
I see.
With all that in mind, we can confidently say that Polaris has considered every possibility and intends to make your residency on Mars as comfortable as possible.
Indeed. We are offering you the opportunity to be a pioneer of Mars in semi-comfortable conditions.
Over the next 10 years, this base won't just be a research outpost. It will evolve from a single pre-established shelter to a thriving, self-sufficient, nuclear-powered ecosystem.